Yeah, so we can get started. So it's our pleasure today to have Tianxin Tang. She's going to talk about one of her recent work on how to design key-nearest neighbor search that hides access query and volume patterns. Thank you so much, Tianxin. The floor is yours.
Okay. Do you know this? I'm not sure about hiding this right panel here. Maybe just leave this here.
Yeah, all we can see is your slides. We can't see anything else.
Oh, okay.
Yeah, it looks good. It looks good.
Okay. So, hello everyone. Okay, I think this. So you will not see the right panel, right? Or you can see that as well.
No, we don't see it. It's good. We just see the slides.
Okay, that's good. Hello everyone. So today I'm going to present a joint work with my advisor, Sasha Botirever, on the topic privacy preserving approximate KNN search that hides access query and volume patterns. So let's get started by looking at what KNN is. It is defined as follows: over some metric space, given dataset, construct data structure that returns a point, which is the i's nearest neighbor of the query point for all I in the range from 1 to k. Suppose all these red points located in the inquiry database and k equals to 2, and we say that P1 is Q's 1 NN, P2 is Q's 2 NN. As we all know that KNN is a basic machine learning technique that has numerous applications, including content-based image search, face recognition, medical diagnosis, and anomaly detection. However, the issue is that nowadays high-dimensional data such as pictures, videos gets more prevalent, and finding the exact KNN suffers the inefficiency problem. And thus we turn to another problem, AKNN, which is appropriate for applications that allow sacrificing some precision for efficiency. Now we define the approximate KNN problem, or epsilon delta AKNN here, and it is defined as in this figure. Suppose k equals to 2 and say epsilon equals to 0.2. And suppose P1 is Q's 1 and the distance between Q and P1 is R1, which is within the radius of the orange circle. And P2 is Q's 2 and the distance between P2 and Q is R2. And we say that P1 and P2 are Q's approximate 1 NN because both locate in the 1 plus epsilon times R1's radius. And then P2 and P3 are Q's approximate 2 NN. Since we have enough background on the problem that we want to solve, we need to establish the problem setting we are working with. Specifically, we are working with the outsource setting, where the client has the data and the secret key. In this illustration, suppose k equals 2 and the client has her secret key. She will first encrypt the database and send to the server. And the server keeps the encrypted database, and on her queries, suppose she is sending the query tag, the blue tag here, and the server will find the approximate 2 NN, in this case, the 2 blue tags that match the query, and send the associated documents back to the client. And such encryption explicitly targets the also setting, offers privacy preserving solutions for accessing the encrypted data, and provides data protection on both the query and the database. And there are multiple works that propose C schemes with KNN queries, and we listed a few references here. But no SE scheme mentioned above provides strong security guarantees, which we say this is because some leak the relative distance of the underlying data point, and some leak the query pattern, sometimes volume pattern and access pattern. I will explain more about this leakage in the next slide. So there are a couple of emerging attacks exploiting common leakage patterns in searchable encryption and have successfully recovered queries or reconstructed the data set. And for volume pattern, we mean that the transcript size of the communication can help the adversary glean information about either the data or the query. And the query pattern is, say, the adversary can tell whether the queries are repeated. And for access pattern, we say that implies the what encrypted file that clients have accessed on the server. And in this case, using the queries, the adversary can know that 2 oranged files have been accessed twice. So just 2 orange documents associated with 1 orange query. And these are the common leakage patterns. And initially, people were okay with such leakage as it provides fast SE solutions. But in recent years, emerging attacks exploiting those patterns. So here is what I included are the graphs at all on the statistical learning of the common leakage files, and also the KPT-19 exploits the KNN patterns that reconstructed the database. So there are other secure SE solutions with strong assumptions. For example, Obelix uses SGX, which has been recently deprecated by Intel on their consumer-grade chips. And also their works that on secure KN scheme relies on non-colluding servers. And so naturally, we ask the following question: can we have a practical secure approximate KNN protocol that hides access secure and volume patterns in an outsourced environment? And you may wonder, can we use ORAM to hide the access pattern? There's a negative result by Navid in 2015 shows directly composing SE with ORAM neither hides the access pattern nor provides an efficient solution. Namely, it costs more bandwidth than transferring the whole encrypted database. But luckily for us, we observed that solving AKNN with ORAM-based constructions is more feasible than general keyword search, since the number of data points or the documents associated with each query tag can be bounded. And our contributions of this work includes defining security of privacy-preserving AKN protocol, PPAKNN, define security of list map with encryption, OMAP, and propose a generic PPAKNN protocol based on OMAP, and then propose OMAP constructions based on 2 oblivious map instantiations. One is based on oblivious AVL tree, and the other is oblivious B skip list. Then we analyze the security of PPAKN constructions and evaluated the constructions through implementations and experiments. So before going into more details of the construction, let's move on to define the syntax, which is part of the standard privilege security paradigm. And AKNN or PPAKN is defined for a metric space and the message space by 2 algorithms: setup, decryption, and 2 interactive algorithms: search and update. And I will just use the illustrations to demonstrate these algorithms and omit the decryption as is more straightforward. For the setup algorithm, the client will input her tags and documents and epsilon and delta, which is part of AKNN correctness, and then auxiliary information Z, which may contain some length information. At the end of setup algorithm, it will output the encrypted database and a secret key, and also the kmax, the largest K supported by the system. The secret key will keep by the client, and the encrypted database will be outsourced to the server. For the search and update, those are the interactive algorithm run by client and server. For the search, the client will input her secret key and the secret K, which is in the range from 1 to Kmax, and the query tag and empty input. And then the server will input the encrypted database at the end of the search protocol. The client will receive the documents and the server will update the encrypted database. The update algorithm runs similarly, but with the exception that the client needs to input an operation type, which is either add or remove. And at the end of the update protocol, it will receive an empty value while the server will update the encrypted database. So for the correctness and efficiency for PBAKNN, we will require epsilon delta correct for search and perfect correctness for both update and decryptions. As for efficiency, we want a big O of polylog in N computational and a big O of polylog in N communication bandwidth, assuming Kmax is much less than N, where N is the number of items in the dataset. And as for the security,
just a question,
yeah.
Tianxin, just here in terms of efficiency, so it doesn't matter. It seems like that it doesn't matter how big the document is, or does N, capital N, includes the size of the document as well?
It doesn't include that. So I would say it's a yeah. So yeah, it doesn't include the size of the documents here.
So does it mean that, I mean, maybe like you will show later, but does it mean that the efficiency is kind of independent of how big the document is?
No, I would say so. It's not independent. So it's just say the size of, you can just think of is the maximum size of the documents, then it will be a multiplicative factor there.
Okay, I see. Thank you.
Yeah. So for the security, we propose a simulation-based security notion with leakage functions for setup, search, and update, and define the real and ideal experiments. And in both experiments, the adversary is given the encrypted database. It can adaptively choose the queries, receive the function outputs, and the transcripts produced by the honest executions of the real protocol in the real world. And in the ideal world, the simulator needs to produce the encrypted database and transcripts based on the allowed leakage. And our definition requires that there exists a PPT simulator for every non-uniform PPT adversary A. It can only distinguish the real and ideal worlds with negligible probability. And this security definition, we model the server as an honest but curious adversary. Once the server is compromised, the encrypted database should be resistant to snapshot attack. No efficient adversary is capable of learning the underlying plain text by examining the encrypted database. And if constructions satisfy our secure definition, then it implies that all PPT adversaries cannot learn information other than allowed leakage explicitly specified in the constructions. So to construct a PBAKNN, we need to study how to solve the unsecured AKNN first. We found in literature that we can solve the unsecured AKNN by reducing AKNN to a list of subproblems denoted by gamma 1 R1 to gamma S RSNN here. We then solve each subproblem with an algorithm called ELSHCRNN. Then we solve the then we can solve the AKN problem. This is a known idea, but with no correctness proof. So we provided one in our work. And we first need to define another problem. It's a bit similar to the problems we have defined before, but it's called approximate near neighbor problem, or CRNN. This is a decisional problem with extra output. So we use a similar figure for illustration. So here is that suppose C, which is approximation factor, that is 1 plus epsilon. C equals to 1.2, and the distance between Q and P1 is R. Then we say that, then suppose this orange circle is radius of C multiplies by R, then we say P1, P2 are Q's CRNN. So how to solve CRN? We use a locality sensitive hashing. Then we will first define what locality sensitive hashing is, then define the extended version of locality sensitive hashing, then describe how to use ELSH CRNN to solve CRNN using ELSH. Locality sensitive hashing is basically a vector of random hash functions, and the closer the data, the more likely they share the identical hashes. And for the extended version of LSH, we denote ELSH. We say that if 2 points share at least one hash, we say that they are close. Otherwise, we say they are far. And we provide an illustration here for clarity. Suppose we're working with the Hamming distance, and these two, I and I prime, are two vectors of bits. And suppose we have H1 and H5 random hash functions, and those orange digits are the corresponding hashes of I. And these are the corresponding hashes of I prime. And we found matches. And we say that for ELSH, these 2 points are close. Well, for the far data, I and I prime, there's no hash match here. And we have the ELSH ready. Let's move to the ELSH CRN algorithm. So for ELSH CRN, basically is to compute the ELSH hashes of all the data points then store in the lookup map. And to solve the CRN problem is we will find CRN of the query points by examining the points sharing the overlapped ELSH hashes as the query point. And the building blocks for our secured version of AKNN is, so we have the ELSH CRNN algorithm and with a lookup map. And also we have an obelisk map with encryption. So both AVL tree and obelisk skip list are known ideas, but their secure definition didn't address the privacy part. So we propose oblivious map with encryption, which address both adaptive obliviousness and privacy of the primitive. So the idea is quite straightforward, is we instantiate the lookup maps used in the unsecured version of AKNN for ELSH CRNN to instantiate those lookup maps with the secured version of OMAP with encryption, and then we can solve the secured version of AKNN. So you can see that for the OMAP-E, the construction is straightforward. We use obelisk map, OEVL tree, and OB skip list implements using non-recursive position-based ORM, and then combined with symmetric encryption, encrypting each blocks and re-encrypting when accessing and writing back the blocks. And you may wonder why, how the oblivious data structures work. So we can, I provide an example. So here is, you can see that in each blocks, there's a tag and associate documents. And together with the tag, tag and the documents, there's also position tags. So position tags are a set of physical addresses that the server can look up to. So those are just to for hide the access pattern. So suppose we are finding the brown query tag here and start by the root node. And the root node, we will first compare the tag, the brown tag with the green one, and say if we find it is larger, we will go to the right path. If it's smaller, we will go to the left path. So here we find that brown tag is larger than the green tag, we'll go to the right path. And then we will just find the right position tag and retrieve it from the server side. So this is a block that is associated with the silver position tag, then decrypted by the client, and client will keep comparing the brown tag with the silver tag, and it finds it finds the brown tag is larger than the silver tag, and will go to the right path and retrieve the block indicating by the brown position tag, and then find the matched tag. And for the OMAP E-access, if we just write it as an interaction between the server and the client, it works as follows. The client will keep her secret key and the root node of the OMAP data structure. It will send the silver tag to the server because it will find the brown tag is larger and go to the right path. And the server will send the corresponding encrypted block, and then send the brown position tag, and it will retrieve the associate encrypt block. We found the matched tag, and finally we'll re-encrypt the blocks and send back to the server. So the security of OMAP E constructions, you can see that it's stronger than structured encryption as it hides the type of the update operations. And then the leakage is for the access is empty, and for the setup it contains public parameters of the oblivious map, including the number of nodes, tree heights, node size, and bucket size, which is part of the underlying ORM. And it hides access queue and volume patterns. And
just a question, sorry, Tianxin, like, so one limitation, as you may already know, of the oblivious data structures that they use oblivious RAM is that they are not dynamic, like in the sense that once you fix the size of the RAM, it's very hard. It's very hard to increase it. It's not trivial, at least. So how do you handle that? Like in the sense that, let's say that you start with 20 documents, you have an OMAP that has some specific size. So, and now you want to add another document that exceeds the size of the instantiated OMAP. So how do you do that? Like, because like you say that you handle updates of documents. So at some point in time, you can imagine that you will exceed the size of the RAM, or do you just instantiate a RAM with very large N, even if you have small documents?
Yeah, we handle it just with a large number of the upper bound N. I think that's a typical usage of ORM. You just have a large N, then yeah, you can say that it's not resizable in that sense. But I'm not sure about, so maybe there's a work for Xu et al. On the size lockable index. So actually, I doubt there's some leakage if the data structure can be resizable, because their work suggests that for their construction is for each update, including even for the deletion, they required an increase, a fixed size of increase in the encrypted data structure. So because for, say, forward and backward security, I would say that resizability probably is an issue here, but we didn't look it further. Yeah.
Okay, I see. So basically you fix at the beginning at setup some public parameter, which is like the maximum upper bound, let's say, and then you work with that. So basically, like why I'm asking is because like all of your efficiency in some sense is function of this upper bound, and it's not actually function of the exact size of your data set in some sense.
Yeah, I would say, but the yeah, it's the upper bound.
Okay. Okay, sounds good.
Okay, for the okay, so let's look at how we use these building blocks in our generic PPA KNN. And so for the client, it will run the key generation algorithm and have her secret key, and it will compute the parameters epsilon, delta, and z, and outputs the EL such parameters and the K-max, the larger K supported by the system. And it will then use those EL such parameters to extract the EL tags. And the tags will be, tags and documents will be used to construct a map. And it will then run the OMAP E setup on the lookup map and keeps the root node on her local storage and the rest of the encrypted data structures on the server. As for the search and update, it will run the OMAP access as a subroutine. And the update will work similarly, just run the OMAP access as a subroutine. And correctness is not straightforward, and we provide a proof on correctness and upper bound on the size of returned results for efficiency. As for the efficiency, the permanent client storage is big O of 1 because we only store the root nodes and the secret key. And the overall bandwidth is big O of K-max times the log square n. And as for the computational complexity, the client will perform AES-based encryption decryption big O of log n times and linearly compute pairwise distance in size of K-max. And the server reads and writes big O of log square n memory blocks for each AKNN queries. And the security of PKA-KNN constructions rely on standard cryptographic assumptions, which include the INCPA of SE and adaptive obliviousness of the underlying obvious map. And it's stronger than structured encryptions to separate the syntax of updates and query as it hides update operation. And the leakage for the our constructions for the setup is the public parameters of OMAP, and for search is the number of executions of OMAP access, and update is the number of executions of OMAP access. The hides X, query, and volume patterns.
So, Tianxin, sorry, yeah, this is Sunny. So you say here that it's stronger than structured encryption, but this is, I don't really understand this statement because ST is a general notion, right? Like you can construct ST schemes that will hide this, right? It just depends on whatever leakage profile your particular construction satisfies.
So I would say this is a I read your latest work, so I would say this is something that is earlier, because you separate the update and the queries by syntax.
Yeah, but you can design schemes like it's just all about the construction. Like you can design a scheme that hides that, right? Like so, it's just about what you want to design. It's not an inherent property of structured encryption.
Yeah. That's probably it's not proper statement here, but I would say it's just I read your latest works that you have something that you combine the update and query to a single access algorithm. Then
right, so that's one example, for example. So that's one construction where we wanted to do that, so we did it, you know. But it could, so it's one example that shows that it's possible to do, right? But it's yeah, again, it's just a question of like what you're trying to design. It's not inherent. It's not an inherent property of the primitive.
Okay, I got
particular construction.
Yeah, okay.
Right.
Tianxin, another question. So this is more about the updates, because maybe I'm missing a part of it. So you are saying basically, like in your algorithm, like maybe I missed some part in the details of the protocol. So basically the time or the number of interactions that the query algorithm or the query piece, like in your protocol, takes is exactly the same number of interaction as of an update.
Yes.
So and this independently of the size of your, so let's say that I update a huge document, like really one of the, like a document that is really big. So you are saying that in your protocol you are accounting, or are you saying that you are making an upper bound on the size of the document? So you are enforcing in some sense that the number of interactions that you will need in both is the same?
Yes, because I would say there's a upper bound on the document size.
Okay, I see.
Yeah.
So this is how you get around and you make sure that the number of interaction are fixed.
Yes.
Okay, I see. Makes sense.
Okay, so we completed our PPAKN protocol, incorporating the ELSH library, ELSH kit, together with 2 new implementations of OMAP, OAV3, and OBSCULY. And then we tested and selected the ELSH parameters on benchmark datasets, which will continue on the next page. So we tested our implementations on the benchmark on the normally used for AKNN implementations. And those were high dimensional data points that are in the Euclidean space. So it's meanness, fashionment, SIF, and GIST. Then we ran the parameter selection algorithm provided by the ELSH kit for 1,000 queries on the training set size of 60,000 and finding, say, the K-max 6 of 10, the approximate 10 nearest neighbors. And we selected the ELSH parameter with low cost, which mean the fraction of number of data points shared, the identical ELSH tags as query, the lower the better, and hierarchical. The fraction that's the number of correct AKN captured in the response set. And also, we found that fixing L equals 10 and epsilon equals or greater than 0.1 across the data sets are sufficient to reach 95% of recall. And we also proposed 2 optimization methods. And one is batch queries, which modifies the search algorithm that aborts the search early if enough points are found. Then this will yield a multiplicative factor improvement in bandwidth. And also for the parallel access, it reduces the number of round trips by the factor, the number of OMAP instances available. And
sorry, Tianxin, but so if you go back to the first optimization, would it be correct to assume that if you employ the first optimization, you are incurring an additional leakage? Because if you decide on the time of stopping the number of interactions as function of the data, it means that you have different stopping times for different queries. So for an adversary who's seeing all of these queries can infer something new.
I would say, so these are not access query or volume patterns.
Yes, it's different leakage. That's I agree with, but it's it's an additional leakage pattern here.
Yes, but also is suppose, because this is the adversary cannot tell how many queries the clients have performed, right? Because this will be a multiplic factor of the, say, for one query. So the client may making 3 queries, and you can't tell whether it's 3 queries or 2 queries.
I see your point, but this is purely intuition. Like I'm just thinking that at some point when you define the security definition, and at some point you need to make an assumption about how long the query is in your batch. Like it can have like maybe 3, it can be 5, or some lambda. So let's say that it's some lambda, then you are saying that for different batches, let's say that it can be like, as you said, the batch can be from 2, it can be 100, who knows. But there is a point where the adversary can say, this one stopped early, and this one stopped way long, it took way longer time. So yes, that's true that the adversary maybe don't know at that point the size of the batch, but it might infer something about it. Okay. And it might infer something. And this is what I mean by it's a kind of like a new leakage pattern. And this is why I just wanted to make sure that I understood correctly.
I understand. So yeah, that's more like a timing attack, I would say. Yeah, okay. So for the efficiency evaluation, this is for the cache size of 10 megabytes. And we have, because we don't have a, so at the time we were writing the paper, we don't have a scheme that is comparable with the strong security. So we can only compare it with a baseline. And the baseline is basically transferring the whole encrypted database. And we have the overview tree E and overview tree E with parallel access, and obfuscatedly E and obfuscatedly with parallel access compared. And we found that obfuscatedly based construction performed better than the overview tree E based ones across the data sets with few round trips per AKN query. And using parallel access reduced the number of round trips by a factor, the total number of OMAP instances available. As for the number of AKN queries reaching the bandwidth of the baseline, and we found that also the obfuscatedly based construction performed better than the overview tree based ones. And both instantiations perform better for SIFT and GIFs, which contains 1 million data points than the smaller data set of minutes and fashion minutes of size 60,000. So this is, say, for optimization, but also Tarek mentioned the leakage may incur more leakage, especially for the timing. Then if you allow this for the optimization with batch queries, it will increase the number of support AKN queries up to 10 times. And for much larger database or a smaller Kmax, offset compared with the baseline increases since the overall bandwidth overhead is below of Kmax time log square n, where n is the, I would say it's an upper bound on the total number of items stored in OMAP. And this concludes my talk. And do you have more questions? I can answer.
Yeah, so thanks, Tianxin. We can thank Tianxin for her talk. Yeah, that was great. Thank you so much. Like, this is really interesting. And yeah, we have time for questions. If anyone has questions, we can use the time.
Yeah, I guess I'd be interested in hearing a little bit more about the security definition and how it's different than previous definitions.
Oh, It's not different. It's because I would say that in our work, we just adapt your STE. So it's just adapting your STE secure definition and then to have our secure definition. And I would not say it's different.
Okay, so the difference is just the particular.
Yeah.
You achieve a different leakage. You achieve a specific leakage profile.
Yes.
The definition is the same. Okay.
Yeah.
All right, makes sense.
Hey, sorry, Sasha's here. Tianxin, don't we have that issue that we had to address about because we have the fuzzy correctness, then we had to modify the definition a little bit?
Oh, yes, I forgot that. Yeah, so so for the probably this is not here, right? Yes, this is not here. So here is for the STE definition, I guess all those STE definitions are for the exact I would say a deterministic functionality. So where the adversary is not given the output, because the adversary can itself compute the output. Are you getting what I'm saying?
Yeah, that's the case for response revealing. Sure.
Not for response revealing, because even for response hiding, the adversary can know the output because it selects itself the input and the database.
Oh, okay. So you mean in the definition, not the adversary in the real world.
So in the definition, the adversary can tell the output, the exact output, because it selects the input and also the database. Say for keyword search, it will know the return result because the functionality is deterministic.
Right. It will know it, but it may not. If it's response hiding, then it may not see it explicitly, but it will know what it should be.
I would say that for the correctness, if it's 100% correct, then it will not see it, but it will know that this will be the return result. Otherwise, the correctness will not be satisfied. Okay. Right?
Yeah, I think we're talking about different things, but
because,
okay. So what's the change then, or what's the change that's necessary?
Because the change here is the approximate KNN is it's a randomized functionality. So if we are not giving the adversary the output, then it will not capture so giving the adversary output is essential in the secure definition.
And Tianxin, I'm not sure we're talking about, there are maybe two issues, right? So I'm not sure we're talking about the same issue, but what I was talking about is that about the issue with so in the simulation-based definitions, it's something like, it's almost like you have the ideal functionality, and that's what the simulator is having, right? So whatever it is, that's the whatever is given to the simulator. And usually it's very easy to define because whatever the protocol is, you have the correctness, you know what the simulator in the ideal world should be given. But since we're dealing with this fuzzy matches, we have the correctness is just provides the bounds, right? So that if it's close, you'll get like there is an upper bound, and if they're not close, there is a probability as bounds, right? So we don't know the exact probability, but we in the definition, one must to ensure that in the real world, in the ideal world, there are the same probabilities of what the adversary and the simulator having, otherwise there is difference. And that's a little bit of an issue because you just cannot simply say for the same inputs what the simulator is given, because it's fuzzy. There is only a bound, right? So that's the issue I was talking about.
I see. Yeah, that's interesting. Yeah, yeah, okay.
It is interesting, and then it's like, yeah. So it usually doesn't come up, but here one has to see how to do it, and the way we do it is that basically, I think if I remember correctly, you have to just run the protocol to just compute to whatever you have to do, because just from basically analytically without dynamically running it, you cannot quite enforce it. So roughly.
Okay. Okay, thanks.
This looks similar to, I guess, what we encountered in our key value store, where the idea, I guess, was similar, right? That because of the race conditions, there was not a fixed output, one output, but there was a probability distribution over the output.
Exactly.
And then it's not clear how to even design your functionality if you have a probability distribution and you do not know what this probability distribution is going to be.
Exactly.
Yeah, and then, yeah, it's essentially like either you're actually running the protocol inside of the functionality to create those outputs.
That's what we did. Yeah, and we did it in another paper on unrelated on the fuzzy private set intersection thing. So we encountered the same issue there.
So is it like you really just run the entire protocol inside the functionality and then
pretty much, yeah.
Yeah, we just not define it that way, because in a sense, it's only the output that is different, right? So it's just we have a auxiliary algorithm that's running the whole protocol, then given to the adversary in the ideal world.
Right. But for us, the problem was also that even if you're running the algorithm inside the functionality, simulator should be given enough information that it can also sort of do the work, simulate the work which is sort of compatible with that probability distribution, and it's not doing something else.
But in our cases, the simulator is not giving those information. Otherwise, the simulator, that will be counted as the leakage, right? So we essentially is running the in parallel, then the simulator will not given those parameters.
Yeah.
Yeah, no, that's really interesting.
Yeah, I think the issue is just because before we are more concerned with all the deterministic functionality, then we don't need to worry about the outputs. But then the functionality we're working with is more versatile, that we will encounter these issues. Do you have any more questions?
I mean, I was also interested in the next slide in your security definition where you talk about snapshot attack. So can you say a little bit more about what you have in mind?
Oh, this is just to justify, because this is honest but curious adversaries. So for some practitioners may think this is not practical or sufficient for address for, say, practical issues. Then we will say that for honest but curious adversary, but it will be resistant to the snapshot attack. And this is actually I would say the natural conclusion for honest but curious adversary, because the adversary can know the encrypted database as just try to glean information from it. Or you are not sure about why we have this here, is it? Or
no, I mean, we had this paper, like, you know, while back when we were defining what we mean really, because you hear a lot of snapshot security everywhere, like, but it's not really precise sometimes what it really means. Is it like a multi-snapshot? Is it an adversary coming at multiple times? Is it coming just once and taking the view of encrypted structure? Like, so we had a definition in that page, so I wasn't sure what you were referring to by snapshot attacking.
Okay, I think this term is just used informally, both in the slides and in the paper. We just think of the adversaries stealing the whole encrypted database.
Okay, makes sense.
Right. So I guess like another question related to this. So in our paper, the way we define, you know, a snapshot attack is exactly this. It's like the adversary gets the encrypted database, but that's it. It doesn't get to see any of the tokens or any of the query protocols that gets executed, right? And then it can have multiple snapshots as well. Like it can have a snapshot after every query, or you know, but it doesn't get to see the query protocol or the token. Okay. So is this what you're you're providing snapshot security in this work, but not, so your security definition is not giving the adversary access to the tokens or the query protocol? It's only the encrypted database?
So no. So I would say this is just a the adversary is given the encrypted database. So this will be the first case you were saying, that in the setup stage, the adversary is given, you can see that the encrypted database.
Yeah. But then so later on it's also going to get
the transcript
view of the query protocol and the other protocols. Okay. So it's stronger than snapshot security.
Yeah, it's stronger than that, but we just make it here is to say that, because some people think this is honest but the curious then may not think that say whether the snapshot attack can be prevented.
Okay.
Yeah. Are there any questions? Additional questions? Okay, if there are no additional questions, let's thank Tianxin for her great talk, and thanks for making the time and presenting your work. This is really interesting.
Okay, thank you.
Thank you.